everyone. My name is Bohong Wang from Zhejiang Ocean University, and welcome to this 18th Energy Visions seminar. Today we are very honored to have Prof. Gunhild Reigstad here to give us a speech about moving towards a low-carbon hydrogen economy, experience and key learnings from national case studies. Prof. Gunhild has 18 years experience in gas technology research, currently working as senior research scientist at SINTEF Energy Research within the fields of carbon capture and storage. It is also known as CCS, hydrogen production from natural gas, and the role of hydrogen and CCS in the impending transition to climate neutrality. Now let's welcome her.
Thank you very much. So let me just start sharing my screen. I hope it shows well now.
Yes, it's quite well.
Okay, great. Then I will start. Thank you very much for the kind introduction. And before I dive into the results, I also want to highlight the fact that it has been a quite broad cross-national group that has worked on the results that have been presented in this paper. So with me, I have a team of researchers from SINTEF Energy Research, from British Geological Survey, Sustainable Decisions, and also Imperial College London from the UK. We have researchers from PSI and ETH in Switzerland, from Ruhr University Bochum in Germany, and also from TNO in the Netherlands. And SINTEF is located in Trondheim in Norway. So this is the outline of the presentation that I will give. And for those of you who have already had a look at the paper, or those that want to read the paper afterwards, you will see that the structure of my presentation is quite one-to-one with the structure of the paper in itself. So before I dive into the main results, I thought it would be good to start taking one step back and contemplating a bit on why hydrogen and why does hydrogen play a central role in the energy system. So why is hydrogen useful? And the starting point for this we find in the Paris Agreement that was reached back in 2015. There, the nations agreed to pursue efforts to limit the temperature increase to 1.5 degrees Celsius above pre-industrial levels. And this spurred the special report from the IPCC on the global warming of 1.5 degrees Celsius. And this report highlighted in a very clear way that the avoided climate change impact on sustainable development, eradication of poverty, and reducing inequalities would be greater if global warming were limited to 1.5 degrees Celsius rather than 2 degrees. So it highlighted the significant benefits of being able to limit global warming to 1.5 degrees Celsius, and it also highlighted that if we are to do so, we need to reach net zero emissions around 2050. And this changed the scope and the mindset of a lot of industries and also governments. Because before this point, one was considering reaching 80 to 95% greenhouse gas emission reductions by 2050. And the sectors and the applications that were the hardest to decarbonize would, in this regime, think that, or plan for being among the few that were able to emit greenhouse gas emissions. When the zero emission target and framework was set already for 2050, this changed significantly the mindsets. And for instance, as came forth in the hydrogen strategy of the EU, it was seen that if one was to reach net zero, renewable electricity was expected to decarbonize a large share of the EU energy consumption by 2050, but not all of it. And one saw that hydrogen had a strong potential to bridge some of the gap, both to be a vector for renewable energy storage and also to decarbonize the sectors that were seen as the hardest to decarbonize. So before, and then as a second introduction part, I think it is also highly relevant just to highlight the hydrogen production routes that we will be including and talking about in this presentation. So on my slide here, you can see 3 different routes. So we have the purely renewable based. If we go from the right hand side, we have electricity being produced from renewable sources such as solar and wind power, and the electricity is fed into electrolyzers and used to produce hydrogen. The second route is stems from natural gas as a starting point that needs to be reformed, so in a reforming step, and then the produced CO2 can be captured up to quite high capture rates such as 90 to 93, 94%, and this captured CO2 can be permanently stored. The third route here goes from biomass that needs to go through a gasification step before it can be reformed. And then if one then captures and separates out the produced CO2 and stores this permanently, we would have what is called a carbon dioxide removal technology. So a technology that is capable of removing CO2 from the atmosphere. And as we will see later, this is also a very useful set of technologies if we are to reach the net zero target. What we saw in the case studies that we have undertaken and from which this paper is based upon is that appraisal of hydrogen as a part of an integrated energy system has many facets and many challenges that needs to be investigated and taken further to fully select an optimal configuration for the hydrogen value chains. So first of all, we need to understand how much hydrogen can be used, where will it be used, and when will it be starting to be used? So how do we need to build up the hydrogen market to serve the end sectors that will need hydrogen? Secondly, hydrogen and CCS chains involves quite some infrastructures that are heavy investments, but with long-term benefits. So it's important that we plan the infrastructure development well, with both in terms of costs and also how we phase the investments to best possible suit the end needs that we have. We need to develop sound business models to make sure that these projects will be established. And we also need to sort all legal aspects such that investors and companies are willing to invest into the hydrogen value chain and contribute and make sure that it happens. We also need to understand that the hydrogen, because hydrogen needs to be produced, it's not an energy source. So we need to understand the full environmental impacts of the production of hydrogen and how it is used into the end use applications to ensure that we reach the greenhouse gas emission reduction targets that we have set. Then, of course, we need to make sure that all safety aspects of hydrogen and the use of hydrogen has been taken care of and are secured, and also that the societal aspects are addressed in each of the projects such that the hydrogen value chains will be a harmonized part of the energy systems. So the results that I will present today are focusing primarily on the first 5 issues, and I will start with the estimation of the hydrogen potential. And I'll show you 3 different examples of how this has been done. So there is no final answer to how one should do this, but rather we want to highlight that there are different ways of doing this assessment, and they all have different strengths and benefits. So the first case here is from a study into the decarbonization of the Rotterdam port area in the Netherlands, which is a very energy intensive area with oil refining, petrochemical, and also power generation as the core parts in this industrial cluster. Here, hydrogen is attractive for high temperature processes. And in the evaluation work, when seeing the potential for hydrogen, one saw that the hydrogen demand profiles strongly dependent upon the details of the upgrading of this industrial cluster. So each high temperature furnace, for instance, that would be upgraded would lead to a significant step up in the demand for hydrogen. So when planning and understanding the hydrogen potential in such an industrial cluster, understanding the individual industries' plans and possibilities, both to perform upgrades and also to invest in hybrid solutions initially to gain technical experience, is of high importance. Another feature of this specific industry cluster is that the future decarbonization would make available off gases from the industrial industries in this cluster that could be used to produce hydrogen. And then, of course, it naturally would have to be combined with carbon capture and permanent storage so that you would achieve the desired decarbonization. And that this produced hydrogen was seen that had a possibility to cover quite a significant part of the hydrogen demand for the industrial cluster in itself. And then, in addition, one would produce hydrogen from natural gas with CCS to cover the remaining demand. Another feature of this specific study was that one saw that it was beneficial to combine industry and power demands for hydrogen. And this is because industry demands are quite stable, while power generation constitutes of a stable and a more flexible part. And when combining these two, the flexible part becomes less significant in the overall system and in the overall structure, so that you reduce the demand for hydrogen storage in the overall system. Next, I will move on to a second approach, and this particular was used on the decarbonization in Germany. And one looked into the 3 different sectors of the industry, the transport and the district heating networks, primarily heating the building stock in Germany. And one looked into how this would develop towards 2035 and beyond. And so this was a quite detailed study that went in detail into all these 3 different sectors. And as you can see on the right-hand side as well, it was undertaken for what is called NUTS 3 regions for Germany. So quite high geographical resolution as well within Germany. So for the industry sector, the steel production was specifically focused upon, as this is a significant industry in Germany, and as well because it has a significant potential to use hydrogen as a feedstock, as a reduction agent within the production process in itself. For the transport sector, a distribution factor that was based upon localization data was established to assess the share of cars, buses, trains, and trucks that potentially could be fueled by hydrogen in the future. And these localization data consisted of the current fleet numbers, mileage or passenger volumes, fuel consumption, the share of diesel vehicles, population density, federal financial aids, gross domestic product, and the income of consumers in each of these regions. And finally, one considered all existing district heating networks within Germany, and where these are fueled by fossils today. One investigated a possibility to change this into being hydrogen fueled in the future. A third approach was undertaken in a case study that encompassed the entire Switzerland. And in this specific study, one wanted to analyze how the entire energy system of Switzerland could reach net zero by 2050. And to this end, one used an energy system model that includes descriptions of all the relevant parts of the energy sector. So as a result, one could see the cost optimal routes for reducing the CO2 emissions to net zero. And as you can see in the left-hand side figure here, we need also negative emissions. So we need to remove CO2 from the atmosphere to actually reach net zero because of a minor remnant of CO2 emissions that were not possible to remove from the emission sources. And on the right-hand side figure here, you can see where CO2 is captured from 2030 and towards 2050. The analysis also gave an overview of how hydrogen would be cost optimally produced within Switzerland and in which sectors. So the lowest figure here and figure A here, you can see how it is produced. So in the beginning, it's produced by SMRs and ATRs, so reformer processes. And then towards 2040, 2050, the share of electrolysis increases. And by 2050, you also have reforming with CCS, and you also have wood gasification with CCS, so the carbon dioxide removal technology to actually reach net zero emissions. On the right-hand side figure at the bottom here, you can see where hydrogen is used. So it starts out in 2030 being primarily used in the industry sector. And then as one moves towards 2050, the transport sector becomes more important. And by 2050, it's the most important sector for the use of hydrogen. Then I will move on to the next topic, which is cost-efficient infrastructure development. And I'll show you two different examples. So this first example comes from a case study on how to decarbonize the domestic and non-domestic heat in the UK. And to this end, an optimization model was used that can optimize the deployment of hydrogen and as well CCS infrastructure, both for production, transportation or distribution, and also for storage. And what became apparent in this UK study was that the storage requirements were a significant part of the overall analysis. And as you can see in the figure A here, a total of 85 terawatt hours were required for the most cost-efficient deployment schedule for infrastructure. And this could be translated into 800 caverns across 4 key regions, as you can see in the figure. And we can compare that to the current estimated cavern storage capacity in the UK, which is approximately 6 terawatt hours. And that is assuming that natural gas caverns can be repurposed to store hydrogen. So this is a significant step up and a development that will need to happen rapidly if one is to be able to go through with the most cost-efficient deployment scheme for hydrogen infrastructure. The study also showed that on the hydrogen production side, the most cost-optimal route was to use ATRs, so reformers, and CCS, and also to use biomass with CCS. So the carbon dioxide removal technology was also needed for this particular study. And then one saw that where one had regions without the necessary cavern storage, then one would be much more reliant on water electrolysis at times of peak demand. And it was not, in this particular study, not possible to go into the details of how this would affect the power system, but we assume that it would have a significant impact on the power system and how this system is set up in terms of storage and regulations. So this would have to be looked into if one does not have the sufficient storage that is needed. The second example that I will show you comes from a study on how to bring hydrogen into the German energy system based on Norwegian natural gas. So here, hydrogen is produced from natural gas that stems from the Norwegian continental shelf, and the produced CO2 is captured and stored permanently on the Norwegian continental shelf. The figure that I have here shows the levelized cost of hydrogen for the transport parts. And this is because this is the part of the levelized cost of the hydrogen that varies between the different scenarios that I will explain to you soon. First, I would like to mention that on an overall level, the levelized cost of hydrogen lies here on 1.54 to 1.55 euros per kilogram between the two different scenarios that we have here. So figure A shows costs for a scenario where the demand in Germany is 5,580 kilotons of hydrogen per year, while figure B shows the same for a scenario where the demand is 3,730 kilotons per year. And out of these 1.54, 1.55 euros per kilogram, the natural gas cost is the main cost contribution. And then the second largest components are the capital and operational costs of producing the hydrogen. But the main focus on this study was to look into the different kinds of options of bringing the hydrogen to Germany. So the two first scenarios here, that is called Euro and All, they come from cases where hydrogen is produced in Norway. The CO2 is directly injected to the storage, permanent storage sites on in the North Sea basin. And the difference between these two scenarios is that in the Euro scenario, the Euro pipe, natural gas pipeline, can be converted to hydrogen. But as you can see, this constituted a very small difference in terms of levelized costs of hydrogen on for the transportation. The three next scenarios comes from scenarios where the natural gas is transported to Germany and hydrogen is produced there, and the CO2 is brought back to the Norwegian continental shelf. And so, as you can see, all these three scenarios have higher transportation costs. And this is because of the volumes of CO2 that needs to be returned to the Norwegian continental shelf. So you can see the H2GER scenario, that is the main scenario where you have pipeline transport of CO2 back to an onshore terminal in Norway. And injected directly from the onshore terminal. The DIR scenario here consists of directly bringing the CO2 from Germany to the continental shelf, omitting the onshore terminal. And the no-PIP scenario here consists of having ship transport of CO2, which could, for instance, be relevant when ramping up the hydrogen production in Germany. And we see that the ship transport has the highest transport costs. Then let's move on to the business development side, because this is a significant part of establishing hydrogen and CCS value chains. And it is important to address the financial risks and also the investment barriers through establishing business models. And what was found in the work was that business model preferences can change with changing business context, as well as with the maturity of the projects. And so the combined selection and assessment process is iterative, but it will follow the steps that you see on this slide. And these steps have been developed based on years of experience on how to establish large-scale hydrogen and CCS value chains. So it has been structured and set up into this process. And on the right-hand side here, you can see the inputs that are needed for each single step. And this assessment methodology was used to undertake a principal analysis of the decarbonization of the residential and commercial heating in the UK. And when focused there on the early stages of the market creation for the hydrogen and CCS infrastructure projects. And what one found was that these projects need the public support. And the business case evaluation of the projects that one wants to undertake needs to be performed in accordance with the 2050 net zero policy adopted in the UK. One also found that a public organization with a clear mandate to coordinate the system-wide business case and deployment across all regions and sectors was necessary to steer and guide and to make sure that one reaches the net zero targets, and as well that the government must be responsible for establishing demand for hydrogen and CCS. And finally, the assessment also showed that a net zero policy must plan for the deployment of innovative carbon dioxide removal technologies to actually reach net zero. Then, as I said earlier, we integrate hydrogen into our energy systems to achieve full decarbonization of the energy system. So it is of high importance that we ensure that the hydrogen that we produce will give us the reduced greenhouse gas emissions as sought. And to this end, life cycle analysis was used within the studies to reveal the overall impact on climate change of the technology options that were available for hydrogen production. And so this is what you can see in the figure here, and you can recognize the three routes of hydrogen production that I shared with you earlier. So we have, first of all, the water electrolysis, where we have around zero here. You can see that solar, wind power, and also hydropower constitutes quite low life cycle greenhouse gas emissions, while if you use power mixes from the grid with high shares of unabated fossil fuels used to produce the electricity, such as the EU mix or the US mix, you would have significant life cycle greenhouse gas emissions for your produced hydrogen. In the middle here, we have hydrogen produced from natural gas reforming. And you can see that here, we have the ATR process coming out the best. And the SMR processes. So here for the ATR, we have assumed 93% capture rate. For SMR processes, we have assumed 55% capture rate. And there are also two different assumptions here in terms of the methane emissions from the natural gas supply chains. And you see the highest emissions here we have for SMRs without capture of the produced CO2. On the right-hand side here, we have hydrogen produced from biomass. And as you can see, the highest levels here of greenhouse gas emissions are related to wood gasification and biomethane SMR, where we do not have capture and storage of CO2. While when we have with CCS, you can see that the life cycle greenhouse gas emissions are negative, and we do indeed have carbon dioxide removal technology options. If we then use these numbers for hydrogen production and also similar numbers for electricity production, we can start estimating the life cycle greenhouse gas emissions for different ways of using the hydrogen. And these results are for the transport sector. So here we have life cycle greenhouse gas emission of an 18-ton truck with different powertrains and across different fuel supply pathways for urban delivery. And the numbers are for today. So you can see here that the first here are internal combustion engine vehicles with quite significant emissions, particularly when we have fossil fuels as the fuel. And then we have the fuel cell electric vehicle as the second last. And here we have renewably based hydrogen production and also hydrogen from natural gas reforming with CCS from around 75 to 125 grams CO2 equivalent per ton kilometer. And the last column here corresponds to emissions for battery electric vehicles. And we see here that the Swiss mix, so the CH mix, solar and wind power here have emissions in the same range as the fuel cell electrical vehicle, while if we use the EU mix for fueling battery electric vehicles, the emissions are significantly higher. So I'll shortly, I'll summarize to you and give you an overview of the drivers of the emerging hydrogen market across these case studies. I'll show you the common opportunities and also give you an insight into the main challenges related to establishing these hydrogen and CCS value chains. Now, I've given you glimpses of the case studies, but before I go on, I thought I would like to give you a brief overview of them, so for your sake of completeness. So the UK case study consists of assessing how to decarbonize UK cities and industrial clusters. It focuses on decarbonization of commercial and non-commercial heat. And it is was closely related to the H21 North of England roadmap, a work that was undertaken at the same time that these case studies were made. The German case study focuses on an overall level on how to decarbonize the gas infrastructure in Germany. And one assessed possibilities for blending hydrogen into the existing natural gas network, the possibility of establishing a dedicated hydrogen backbone, and also the possibility for establishing a CO2 transport network to transport CO2 towards the Norwegian continental shelf for permanent storage. The Dutch case study focused on how to decarbonize the Dutch economy using the Rotterdam port area as a starting point, but then also going beyond and assessing also the impacts of wind power and the possibility to produce hydrogen from wind power. Then we have the Swiss study that looked into how to decarbonize the entire Switzerland and reach net zero emissions by 2050, and particularly also how to provide CO2-free transport in Switzerland. And then finally, we have the Norwegian study that looked into how the Norwegian full-scale CCS chain could give synergies with hydrogen production and how hydrogen could be produced for export to Europe and also globally. So then to look into the key drivers of the emerging hydrogen market. So what we saw is that the industrial demand for decarbonization were key drivers in all of the case studies. And we see that the industrial demands are quite significant in volume, which will also bring the hydrogen chains that are being established to the full scale, which in turn has give the possibility to reduce the costs by scaling up. In the UK, as I mentioned before, decarbonization of the domestic and commercial heating is a central driver. And this is because the significant share of buildings that are connected to the existing gas network. And it is a sector with large needs for energy storage and the flexibility also to accommodate seasonal variations. And in this perspective, hydrogen becomes particularly of interest. In Switzerland, the freight transport sector is the second most important sector for the hydrogen market development, while this was different in the other countries, for instance in Germany, where the transport sector would benefit from a hydrogen value chain being established. And then one also saw that, for instance, in Switzerland, hydrogen played an important role in the seasonal balancing of the Swiss power system. And then for the Norwegian case, the export option is the driver for hydrogen production. While undertaking these 5 studies, we also saw that there were some common opportunities in these emerging hydrogen markets. And the first of all is that since we saw that the industry sector is the main driver on the hydrogen demand side, one needs hydrogen production that can scale up fast enough to meet the demands. And one saw that where you have natural gas available, hydrogen production via natural gas reforming with integrated CCS would provide this option. And you can scale up fast enough and also then contribute to bringing down the costs, both for infrastructure that can be fully utilized because of the full scale of production and use, and also for the rest of the hydrogen and CCS value chains. We saw that we need carbon dioxide removal technologies, and these mainly need as the possibility to permanently store CO2 that has been captured either from air or from biomass. And when you establish integrated hydrogen and CCS infrastructures, you also provide an easily accessible pathway for transporting CO2 from carbon dioxide removal technologies to storage sites where the CO2 can be permanently stored. And finally, we saw that collaboration across the international borders were in many cases beneficial or necessary for the realization of the business cases. And for instance, we saw that for the cases of the German CO2 transportation, storage on the Dutch continental shelf was seen as highly attractive, and also for CO2 captured in Switzerland in the near future to midterm future, it is highly relevant to be able to transport this to the North Sea basin for permanent storage. And finally, also the German case study also assumed the possibility to import hydrogen from Norway. Then to close with a little bit on also the challenges for establishing hydrogen and CCS value chains, because these are technologies that needs a significant scaling up and significant deployment rate to be able to establish a value chain as desired. And we see that the main challenges are related to how to develop and initiate the hydrogen market. And we see that this will require government intervention, both at country and also at EU levels here in Europe. And for the European countries, it's of course important that these are coherent. We also see that hydrogen is attractive in a net zero framework, and therefore it's important that there is coordinated planning, governance, and decision-making frameworks to both establish net zero policies and also invest in infrastructures for hydrogen and CO2 that can help reach the targets. And then finally, an EU-wide effort in Europe is needed to simplify the legislative pathway for hydrogen and CCS value chains. So to summarize, we have seen that it is highly beneficial if we are able to limit the global warming to 1.5 degrees Celsius, and then we need to reach net zero greenhouse gas emissions by 2050. And hydrogen becomes very attractive within this framework because it can decarbonize emissions that are hard to electrify. We have seen that the industry sector is the key, the most important driver for establishing the hydrogen markets, but also decarbonization of the heating sector and also the transport sector are very important. And seasonal balancing is also of essence when going for the net zero greenhouse gas emissions energy system. We have seen that net zero policy frameworks are needed for the hydrogen markets to emerge, and we need governmental coordination of efforts and also investments in infrastructure for hydrogen and CCS. And finally, we've seen that the capacity for hydrogen to reduce greenhouse gas emissions hinges on the energy system where the hydrogen production occurs. And particularly, this is important for electrolysis, for the power used in electrolysis, and also the CO2 capture rates and the permanent storage for reformer-based routes. And with that, I would like to acknowledge the sponsors of our work, and I would be happy to take questions.
Thank you. Now we have a question from the chat. It is said that hydrogen generated from renewable energy is clean, but is also cost-consuming. Will it still be a promising solution for hydrogen generation in the future? And how can we improve this situation?
This is a very good question. So thank you for raising this. I think there are several aspects to this, and I think the most prominent is that we expect globally that the cost of renewable electricity will go down because of these technologies being under development. So we have what is called learning by doing effects. So the more we invest in these technologies, the more we're able to cut the costs and to bring down the costs here. So I think that in the long term, we will see costs going down. And I think we also need to have in mind that cost is always a relative thing. So it is also a question of what the alternatives are. And I think that's also why we see that CCS plays a significant role in the total picture, because in the cost picture and the context of costs where you are to reach net zero, you will have to deploy quite a few costly measures, but it is even more costly not to reduce the greenhouse gas emissions, so to say. So I think it's also a question of how you set costs up against each other, and the cost picture on an overall level. So I think that renewables will definitely be the most important hydrogen route going towards 2050. We have a lot of deployment of renewables before then to bring down the costs and also to decarbonize the power sector, which is absolutely important.
Yeah, thank you. And do we have other questions from the audience? Actually, I have one question. As we all know, the producing of hydrogen, if we use electrify, it will also cost some water. And what will it also cost? It is also a huge amount of water if we use to generate a lot of hydrogen. Do we need to consider this, and how can we yes.
Yeah, that's also a very good question when it comes to the electrolysis route. So I think that one would definitely have to consider using seawater for the electrolysis, but then you have the additional component of desalination that you would need to undertake. I believe that there is also research going on how to use seawater directly for electrolyzers, but this is not my an area where I have deep insights, unfortunately. And then I guess one would also have to look into how one can where water is available, and if there are ways to how can I say, to use some kind of waste water or other ways of utilizing water without going against the water that is needed for the rest of the society.
Thank you very much. Any other questions?
Hello.
Yes, please.
Thank you for your good, wonderful speech. I have a question about the how to quantify the intervention effects of governments in your research.
Yes, that is a very important aspect. We have, in the case studies that we have undertaken here, we have mainly looked into what is needed, what must be in place for these hydrogen and CCS value chains to be established. So we haven't looked into that much how much intervention you need, basically. So we haven't quantified it as such and looked upon the consequences of lacking support and development. So we've mainly kind of set up the requirements to reach the more optimal solutions.
Okay, thank you for your response. Thank you.
And we got another question from the chat. That E2 heating is more efficient than E2 hydrogen. So does the thermal energy storage have opportunity in carbon reduction?
Yes, this is a little bit on the side compared to what we have been looking into. But in the kind of on a general level, thermal energy storage does definitely have a role in reducing carbon emissions. So I think that when we now seek net zero greenhouse gas emissions, it's paramount that we use the energy available with the highest possible energy efficiency. So where you have low temperature heat demands, you would definitely not go for hydrogen. You would go for other options. And this could also include, for instance, heat pumps going from electricity to heating, or other ways of geothermal storage, for instance, of heat. So hydrogen you would primarily use for high temperature heating, so furnaces and industries that needs heat at quite high temperature levels, where electricity heating is not feasible.
Okay, thank you, Prof. Gunhild Reigstad. Do we have any questions from the audience? We also have another platform if there are any questions. Okay, thank you very much, Prof. Gunhild. Thank you for your very interesting and informative speech. And thanks for coming to this 18th Energy Vision seminar.
Thank you for the opportunity to share.